Okay, guys, let's begin. So we're gonna begin the last module now, the last unit of discussion. And as I mentioned earlier, we're going to study two other types of functions. We're gonna study exponential and logarithmic functions. Before we discuss this, we need to talk about composition because we need to know the idea of an inverse function. Okay? Because these two functions they have a special relationship among themselves. They are inverse of each other. Okay? So to understand this notion of inverse, we first need to talk a little bit about composition. So that's the plan for today. Composition, inverse, and then we introduce exponential and logarithm. Next class, we're going to talk about properties of logarithms, and we're going to solve exponential and logarithmic equations. Okay? And that's the plan for what's left of the course. Okay, so let me start with an example. So even though we have not called this composition, we have been doing composition of functions. Okay? So, for example, if I ask you to find this, you know exactly what to do. So find f of 2x plus 1 if f of x equals x squared. So what do we do? If I ask you something like this,
You substitute f of x f of 2 into x.
so you replace x by 2x plus 1, right? So here, you know, this is very straightforward. All you have to do is plug in. Instead of x, you put 2x plus 1, and then you evaluate this. So we get 4x squared plus 4x plus 1. Right? Okay, now what if instead of giving you this, I actually give you the function. The function f is x squared, and then notice that this is actually another function. We can call it g, okay? 2x plus 1. So as a second example, I can ask the same question in a different way. I can give you the function f, and then I can give you another function g, which is 2x plus 1, and then I can ask you to find this. Okay? So again, basically what I'm telling you here is plug in the function g into the function f. In other words, wherever you see an x, you put g. Now, what is g? 2x plus 1, and that's exactly the same as problem number 1. Does anybody understand this? So this right here is just g of x squared, which is then 2x plus 1 squared, and as you know, is 4x squared plus 4x plus 1. Questions about this? So what we just did here, this is called function composition. To compose the function is basically just to put a function inside another function. That's all it is, okay? So, you know, there is a little picture that you can have in your mind when we have something like this. So this is called composition. The composition of f with g. And then, for example, remember, you can think of a function as a little machine. So in this case, the input is x and the output is f of g of x. So what's the first function that you apply to the input? So when you plug in a number x, what's the first function that acts on this x? Is it f or g? G acts on this input, whatever this is. Then the output of g works as the input for the function f. Do you understand this? So this is like putting two machines one next to each other. Okay, the input comes here, this machine does something, give you an output, and then that output goes into the next one, okay, and then give you the final one. So you can think of this, you know, it's a little figure like this. Here we have the function g, here we have the function f, and x comes here, then g of x comes out, that goes into this guy, and then f of g of x is what we obtain. Is this clear? This is called function composition. Okay? So I guess let me give you the definition. You know, there are some technicalities that you need to take into account. For example, technically speaking, you cannot really compose whatever you want because there is a, you know, a certain requirement that must be satisfied. First of all, okay, so the domain is a subset of the domain of G, but you have to make sure that the output of G, so the range of the function G, has to be a subset of F. Okay? Because, you know, if G gives you a value that's not good for this function, then this machine is going to break. You understand what I'm saying? So it doesn't mean you cannot do whatever composition you want. So most of the time, you just plug in and then you analyze and figure out what's the correct domain. So when it comes to the time to figure out what's the domain for a composition, you have to be careful. It's not just figuring out what X has to be for G, but you also have to make sure that whatever the output is for G is okay as an input for F. Okay? So there are several things that you need to take into account when you think about the domain of a composition. All right, but anyways, let's define this. So definition, let y equals f of x and y equals g of x be two functions. Be two function so let's say the range of G is a subset. So subset means contain, okay? It's a subset of the domain of F. Okay, so then there's a new function that we can define. Now this is the formal notation that we use. Okay, so put the two letters with a little circle in the middle and then of X. So this notation means F composed with G. Now, what does this mean? We define this as F of G of X. Okay, but the formal notation for composition is this is the symbol that we reserve for composition. So then when we do this, this is a function, okay? It's a well-defined function with those conditions. It's a function for the composition of F with G. Do you understand this? Now let's do a little example. For the same functions that we have above, let's say that we have the function f of x equals x squared and the function g of x equals 2x plus 1. But now this time, let us find g composed with f. So let us find this. Okay. So in other words, if you want to figure this out, what is it that you need to do? So g composed with f. This time, the outside function. So when you have a composition, this guy is called the outside, and this one is called the inside function. Okay, and it should be clear why they're called outside and inside. Here I switch them. Okay, the outside is G and the inside is F. So that means literally plug in the function F into G. So what expression do I obtain if I do this? What do we get? So we get 2x squared plus 1. And the reason why I did this little example is just to let you know that composition is not commutative. The order in which you compose the functions matter. Notice that when we did f composed with g, in the sample above, what function did we get? 4x squared plus 4x plus 1. Yes? Now, if you switch them, if you do g first, okay, if you do g composed with f, then we get something completely different. 2x squared plus 1. Okay? So in general, the composition, the order is very important, so they don't have to be the same. So note, in general, f composed with g is not necessarily the same as g composed with f. Okay? There could be cases in which it doesn't matter, but in general, these two things are not the same. So the order in which who goes first, who goes here and who goes here matters. Okay, questions about what function composition is? It's just putting a function inside another function. Okay, that's all it is. Okay. All right. So let's do another example. This example is so that we introduce the next idea. So consider this function 2x plus 1, and then the function g, which is 1/2 x minus 1/2. Okay. So find the following. So first, let's find f of 1, and let's find g of 3, and let's find f of g of 3, and then, oh, that's good enough. And then finally, we're going to find f composed with g. Okay. All right, let's see. Try this. So what's the answer to the first one? 3. Good. Everybody okay? All right. So what's the answer? What's the answer to the second one? 1. Very good. I guess let's do a little computation here. So when you plug in, you get 3/2 minus 1/2, which is 2/2, which is 1, right? Okay. So now what's the answer to the third one? To C. So here we have f of g of 3. So what's g of 3? We already did in part B, right? So that's f of 1. And what's f of 1? We already did it in part A. That's 3. Does everybody understand this so far? Okay, so let us notice what's going on here, because there's something interesting happening. So notice that, for example, if you look at part C, what happened? We plug in 3, right? That was the input. And what was the output? What was the final output? 3, okay? So something is going on here. So here we have the function g. Here we have the function f, right? And then what we are seeing is that 3 is coming in, and then, a 1 comes out, but then this 1 goes in, and then 3 comes out. So if you focus here, remember, all of this is one big function. So you can think of this as one machine, right? And then inside that machine, there are 2 little machines working in series, okay? So let's say that you don't see what's going on inside the green box. Then what you observe is that 3 comes in and 3 comes out, okay? Now, let's see. We want to test it with something else. For example, let's test it with 0. Let's say that 0 comes in. What's going to come out of 0? If 0 goes in, what will be the output on the other side? Let's see. Let's evaluate what goes inside the little machine. So 0 goes into the big machine. That means it goes into G first, right? So what's G of 0? What's G of 0? Negative a half. And then negative a half goes into F. What's F of negative a half? So you put negative 1/2 here, so you get negative 1. Negative 1 plus 1, you get 0. So what can you say that it appears to be happening? So let's say that we don't see inside the machine yet. So what seems to be happening?
They seem to be going in.
For example, if I plug in 5 here, what do you think we're gonna get here? 5. So what's happening? The same input happens to be the output, right? Whatever the input is, that's gonna be the output. Whenever this happens, we call this the identity function. I mean, this function is the function y equal x, right? The function y equal x is the one that tells you whatever the input is, that's exactly the output that you obtain. Yes? So what we can say is that it looks like this is the function y equal x. Yes? Now, we have another name for this little box. What is this name? That's the composition of f of g. Of f and g. So we know that this box is this function. Okay? Now, it looks like when you do this composition, we are actually getting the identity function. So let's see. That's part D. Let's compute it. Okay? So let's do part D. So we want to do f of g of x. So that's f of g of x, and then, plug in. So that means that we need to plug in g into f. And then put the formula for g, which is 1/2 x minus 1/2. After distributing, So we're gonna get x minus 1 plus 1. The ones cancel out, and we get x. So the moral of the story is that indeed, if you do f composed with g, you're gonna get back x. In other words, whatever input comes in, that's exactly what comes out. Do you understand this? Okay? This doesn't always happen, as you saw above. Okay? I mean, this is a very special situation. Above, in the example we're doing, this didn't happen. Now, whenever something like this happens, that you have two functions, and when you take the composition, you obtain the identity. What we're saying here is that basically these two functions, they're canceling each other. You see? G is doing something, and what's the job of f? What is f doing? It actually takes whatever G did and undo. Okay? So G takes 3 into 1, and then f takes 1 back to 3. Okay? So whenever this happens, that the functions, they cancel each other or undo each other, we call these functions inverse of each other. Okay? So we say, in this case, we say that f is the inverse function of G. And now if you flip them and the same sort of situation happens, we say that G is the inverse of f. Okay? So, let's say here. So note. So the question is, if we flip them, the same thing is going to happen. Let's see. If I compute the other way around, so we get g of f of x. So this time we get 1/2 f minus 1/2. So that's 1/2 times 2x plus 1 minus 1/2. So that's x plus 1/2 minus 1/2. So we get x as well. Okay? So in other words, this line right here is telling me that f cancels g. This line here is telling me that g cancels f. Do you understand this? Okay? So whenever this happens, we say that these two functions are actually special. We call them inverse of each other. And instead of using the letter g, for example, we have a special notation for the inverse of f. Here is a little fact, and I guess it's last challenge for you to try to do it on your own. Prove that the inverse is unique. In other words, if a function has an inverse, it can only have one inverse. You can have a function with more than one inverse. Okay? So let me first make a note here. So whenever this happens, so we say that f and g are inverse of each other. Okay? So f and g are inverse of each other, and then the fact and the challenge for you, if you want to try to do it at home, is to show that if a function has an inverse, it can only have one. So the inverse is unique. The inverse function is unique. In other words, a function cannot have two inverses or more. Okay? If it has one, it may not have an inverse, but if it has an inverse, it has to have one. Okay? So because there is only one inverse, we actually have a special notation for that. We write, instead of writing the function g, what we like to write is this. Okay? So when you write this is -1, this doesn't mean 1 over f. Okay? This is a notation for the inverse function of f. Okay? This is, so we write this as the inverse function of f. So in math, whenever we have a certain object that only, that is unique, that exists only in one instance, then we typically give it a name. We have a special notation for that. Okay? Like for example, there is a unique number. Given a positive number, there is a unique number, or actually any number you want, any real number. There is only one number, so that when you add it with a, you get 0. That's called the additive inverse. And we have a notation for this. How do we write this number? How do we formally write this b? Minus a. So every time that, for example, when you write -2, what you're telling me is that this is a number, this is the only number, so when you do 2 plus this guy, you get 0. That's what that minus represents. Okay, that's where that's coming from. Okay, anyways. So that's what an inverse is, and this is what we want to focus on because, again, as I mentioned, the two functions that we're going to study, that what they have, the property that they have is that they cancel each other. They are inverse of each other, okay? And the idea is that once you know enough information about the function f, you can get for free or deduce a bunch of information about f inverse. Like if you know how f looks, then f inverse, you get the graph for free, and all of that. There are many things that you can deduce automatically, okay? So let us look at these properties a little bit more closer. So now we know what composition is. I just defined to you what's an inverse, so I guess let me write the formal definition. So definition, let y equal f of x and y equal g of x be two functions so that when you do f composed with g is equal to x, and the other way around as well, okay? And g composed with f is equal to x. So you have two functions and this happens, then we say that they are inverse of each other, okay? Then we say that f and g are inverse of each other and we typically write g of x, we write it as f inverse of x. Or the other way around, you can write f as g inverse of x, okay? Doesn't matter which one. Okay, so that's our definition. Now the question is, another question is, okay, we're defining this idea. Now, does every function have an inverse? This is another question to ask, okay? So we're defining this notion. So then, is it true that if I give you a function, you are always guaranteed to find an inverse? So let's try to address this question. So question, given a function, so given a function y equal f of x, does it always have an inverse? Okay, all right, let's see. So actually, let's try to answer this question by looking at an example. So I'm going to give you two examples, very naive, very easy example. And then we're going to try to see whether the answer is a positive answer or is a negative answer to this question. And then, of course, whatever we answer, then if we say no, then we need to say, okay, then what condition must be satisfied, must f satisfy to ensure that it has an inverse, okay? But let's first, maybe the answer is yes, okay? So let's look at the following example. Let's see. Remember, functions are relations, so, if I just give you a relation, then we're good to go. So let's look at this, and this, and let's say that this is the function h. Okay, so by doing this picture, I'm saying that h is a function that takes element from here. This is the domain, 2 elements from here. How? As follows. So 2 goes to 7, 3 goes to -1, 4 goes to 2, 5 goes to -1. Okay, it's a function. Remember, to be a function, all you need is that one input has to have only one output. Okay, so you cannot have two arrows having the same source. You cannot have two arrows coming out of the same place. That's not happening here, right? So every arrow, they come out of a unique place. Even if these two guys go towards the same place, they have different inputs. So that's fine. Do you understand this? It's a function. And then, let's write another one here. Again, same domain, same codomain. So let's call this one f. And then let's do 2 goes to 7, 3 -1, 4 goes to 2, 5 goes to 8. Then just let's do that. So first of all, what's the difference between f and g? Between f and h? Sorry. What's the difference between f and h? Yes?
H5 goes to -1 and F5 goes to 8.
Okay, so these are different functions. Do you understand this? Okay, good. Now, we are trying to figure out whether these functions are going to have an inverse or not. So let's see. If h is to have an inverse, what is this inverse supposed to do? What is the inverse supposed to do? What's the job of the inverse? Look at the picture again. What's the job of the inverse function? So to undo whatever the original function does, right? To cancel the original function. In other words, if the function h sends 2 to 7, if we have an inverse, what's the inverse supposed to do? It's supposed to send 7 back to 2, right? The inverse is just this nasty function that, I mean, it's not really nasty, it's actually very nice, but it's this function whose only job in life is to undo whatever h does. Okay? That's what the inverse does. H sends 2 to 7, the inverse says, no, you go back to 2. 3 to negative 1, no, you go back to 2. Do you understand this? Okay? So, if there is an inverse, okay, it will be a function that goes this way. Yes? Now, let's see what this function is supposed to do. This function is supposed to send 7 back to 2. It's supposed to send, let me do this one first, 2 back to 4. But then, okay, A ignores it because A is not even part of the range of H, right? We could even erase the 8 here and then, so A is like if it didn't exist, so it ignores the A. So I guess we can even do this if you want. But then what happens when if this were to be a function, right? Then what happens when it hits negative 1? What is it supposed to do? What is it supposed to do?
Supposed to be 3, 4, 5.
Right, so it's supposed to do this. You know, but it can also do this. Do you understand this? So for example, as a relation, I can actually do solid lines. As a relation, that's fine. So every function, and if you want, every relation has an inverse. All you have to do is, flip the order pairs. Remember, relation is just a set of order pairs. So the inverse of a relation, you just flip the order pairs. Does that make sense? So in other words, if a function or a relation goes from the left to the right in this picture, the inverse relation will go from right to left, just flipping the arrow. That's all it does. Now the question is are these arrows, green arrows, representing a function? Are the green arrows a function? Why not? Okay, but there is no graph here. So if you say vertical line test, then you need to graph and justify. There is a very easy way to say this. Yes?
The 2 arrows coming from the same place.
Exactly. If we have an input that has 2 different outputs, that's impossible for a function, right? That actually violates the definition of a function. So here we have negative 1 that has 2 different outputs. Okay? So I guess you could write this down, but notice that this is a relation. Okay, it's the inverse relation of H, that's fine, but it is not a function. Why? Well, because negative 1 is related to 3 and 5. Do you understand this? So H is a function, but if you look at it as a relation, then its inverse relation, if it's going to have an inverse, it has to be the green one, but it's not a function. So not every function has an inverse function. Do you understand this? As a relation, they do, but as functions, not every function has to have an inverse. So we can immediately say that the answer here is no. Does it always have an inverse? No. But then, of course, the follow-up question is, okay, what condition must F has to ensure that an inverse exists? For example, let's look at F here, the one on the right. If we have an inverse, once again, what is the inverse supposed to be doing? Just flipping arrows, right? So F inverse is supposed to go this way, and then you do this, this, and this. Now, is this a function? The black arrows, do they represent a function? It's a function. So this time, F inverse is a function. Because the same input, every input has a unique output. Okay, we don't have an input going to 2 different outputs. So now let's try to see what's the difference between H and F once again. Okay, because Here we have a function that doesn't have an inverse as a function. Now we're talking about function, not relation anymore. Here is an example of a function that doesn't have an inverse function, and here is an example of a function that does have an inverse function. So let's try to find what, what property or what extra property or condition is f satisfying that h is not doing. Or the other way around. What is h? What's happening in h that's not happening in f? So who can tell me? I asked that at the beginning, now I ask it again. What's the difference between h and f? You answered earlier, so make sure that somebody else can answer this. Yes?
Every y value is so unique like x value.
For whom? That's not true for h. I asked you what's the difference between them. You say every y value has a unique x value. For whom? I don't know.
Each like two x values share one y, but each y value has like each x value.
Okay, yes.
For F, every input has only one output, while for H, some inputs have two inputs can have the same output.
But that's I mean, to say that every input has only one output, that's the very definition of a function. So both f and g are satisfying that condition. Yes.
For h, there are two x's that come out to be the same y, but for f, they don't have that, so when you switch them, the same y has two x's.
Okay. So, but let's not talk about switching. Let's talk in the same direction. So.
Okay, so then for h, two x's have one y, but then for f, they don't have that.
So in other words, what properties h is f does f has that h doesn't? Every time that you have two different x's, right, for two different inputs, any two different inputs, you are always guaranteed to have different outputs. Yes? If you have two different inputs, you are always guaranteed to have two different outputs. While in h, we cannot say that, because we have an example of two different inputs, namely 3 and 5, going towards the same place, -1, same output. Yes? And that's what creates a problem, because if you try to flip the arrow, what's going to happen? That same output that they go, when you flip the arrow, then it's going to give you two arrows coming out of the same place. Yes? If you have a function for which two different inputs always go to different outputs, you're going to have this other situation that arrows look like this. Right? So when you flip them, then they're going to be nice arrows also. They're not going to have the same source. Does that make sense? So we have a name for this type of functions. Okay? Functions that behave like this, that two different inputs have different outputs, we call them one-to-one. Okay? Or injective. Injective is a fancy word, but typically, text call it one-to-one, but mathematically we really call it injective. Anyways, a function is injective or one-to-one if anytime that two inputs are different, then the outputs must be different. Okay? And that's the condition that we need if you want to talk about the inverse of the function. Because if a function fails to be one-to-one, then that means that you're going to have this other situation, that different inputs will go to the same output. Then if you try to flip the arrow, you are in trouble. Do you understand this? So f is an example of what we call a one-to-one function. So here we say that f is one-to-one. So this is an example of a one-to-one function. And I'm going to write the definition now, but basically a one-to-one means that if x1 is different than x2, then f of x1 is different than f of x2. Okay? So every time that you have different inputs, then you're guaranteed to have different outputs. An equivalent statement would be that if two outputs are the same, it's because the inputs must be the same. We're going to use this idea to, for example, solve exponential and logarithmic equations in some instances. Okay? That's called the contrapositive of this statement in logic. Anyways, the point is that this is an example of a one-to-one function, and notice that we have an inverse, and this one is not one-to-one. Okay? So this one is not one-to-one. Since 3 is different than 5, but h of 3 equals h of 5. Okay? So this is now one-to-one because we have two different inputs giving you the same output. Okay, so let me, I guess, write that somewhere else. It looks a little bit strange. So say this is now one-to-one. By the way, sometimes we just write this for one-to-one, just for sure. Not one-to-one, since obviously 3 is not the same thing as 5, but when you evaluate them, they yield the same output. Okay? So, and the point is that if you want the inverse to exist, we need this behavior that different inputs have different outputs. So then you're free to flip the apples. Okay? And then you don't encounter any issues. So yes, let me define this. So definition, a function y equal f of x is said to be one-to-one. Let me say here in parentheses, or injective if for any two distinct inputs, we get distinct outputs. So more formally, in other words, if x1 is different than x2, then f of x1 must be different than f of x2. Okay, so that's what it means to be one-to-one. For example, I guess let me show you how you can figure out whether a function is one-to-one or not by using this definition. And I would say here equivalently, because this will be useful later. So equivalently, one-to-one means that if f of x1 equals f of x2, then this can happen only if x1 is actually the same as x2. Okay? So these two statements, they mean exactly the same. Okay? For example, if it is cloudy, then it will rain. An equivalent statement is if it's not raining, or if it doesn't rain, then it is not cloudy. You understand what I'm saying? So if you assume that the truth value of the first statement, then that implies the second value is also true, and also the other way around. Okay? So I repeat, if it is cloudy, then it will rain. That's equivalent to say if it's not raining, then it's not cloudy. Because if it was cloudy, it should be raining. Do you understand this? Okay, so that's exactly what I'm saying here. So if x1 is different than x2, then f of x1 is different than f of x2. The contrapositive, which is an equivalent statement, is negation of this implies negation of this. What's the negation? F of x1 equals to f of x2, then that means these guys, they better be the same. Okay? So the only way that you can have the same output is if you started with the same inputs. That's basically what we're saying. We're going to use this to solve equations later, as I mentioned. And, for example, if you want to determine whether a function is one-to-one or not algebraically, okay, this is better to work with than the original definition. So, I guess, let me show you a little example. For example, we have the function 2x plus 1, right? We showed that that function has an inverse. Namely, what was it? 1/2 x minus 1/2. So that function better be one-to-one, right? Both of those. So, let's show it. So show that f of x equals 2x plus 1 is one-to-one. Okay, so to argue this, we need to show that if you have two different inputs, then the output must be different, or equivalently, if two outputs are the same, then the input must be the same. This is easier to do when you are dealing with equations. Okay, so indeed. So, suppose that you have f of x1 equals f of x2. So that means that 2x1 plus 1 must be the same as 2x2 plus 1, right? And now just, cancel stuff. So you get 2x1 equals 2x2. The 2's cancel, dividing by 2. So we get that indeed x1 is equal to x2. In other words, if you have two outputs that are the same, then that implies that the inputs must be the same. Okay? So, but then of course, if the function is more complicated, the formula is more complicated, then doing this is a little bit, more algebraically involved. So f is 1 to 1. So what we want to do is be able to determine whether a function is 1 to 1 or not. But for example, how about from the graph, from the picture? Remember, we had a very easy way to determine whether a relation was a function or not if I give you the graph. What was it? If you see a graph of a relation, how do you determine whether it is a function or not? You use the vertical line test, right? It's something very easy and visual that you can determine. Now we have something similar for functions that are 1 to 1. There's something called the horizontal line test, okay? And basically the horizontal line test, what it does is it tells you whether a function is gonna be 1 to 1 or not. Because basically, when you draw a horizontal line, what is it that you're doing? You're fixing a y value, right? And if your horizontal line crosses the graph at 2 points or more, what are you saying? There are 2 different x's, or maybe more, that have the same y. So automatically, it's not 1 to 1. You understand this? So if you want a function to be 1 to 1, that means any horizontal line, if it's going to cross the graph, it can only do it at 1 point. Okay? If it crosses the graph at 2 or more, that's it. It's not 1 to 1. So that's called the horizontal line test. Let me write it down. So first, the theorem that says that, you know, as we discussed above, if a function is going to have an inverse, it has to be 1 to 1. So if so a function y equal f of x has an inverse if and only if it is 1 to 1. Okay, so it's very important to know when a function is 1 to 1, so we have a nice characterization, at least if you know the graph. So this is another theorem. This is called the horizontal line test. So horizontal line test. So a function y equal f of x is 1 to 1 if any horizontal line intersects its graph at most once. So when I say at most, I mean that maybe it doesn't intersect at all, okay? But if it's going to do it, it can only do it once, okay? In other words, an equivalent way of saying this is, if you can draw a line, a horizontal line that crosses the graph at 2 points or more, then that's it. It's not 1 to 1. Do you understand? Okay. So, let's see, do an example. I'm going to give you some pictures and you tell me the functions represented by these pictures are 1 to 1 or not, okay? So, determine if the given functions are 1 to 1. Okay, so let's see, let's do this guy. What do you think? If you were to pick a formula for this shape, what would you say? It's squared. I mean, it could be something else, right? 2x squared or whatever, but I don't know. Let's say x squared. And let's do this one. If you were to pick a formula for this, what would you say? X cubed. Then so this one. And if you were to pick a formula for this, what would you say? Square root of x, right? Okay. So what do you think? Number one, is it 1 to 1? Why? Right? For example, I don't know. I can draw a vertical line right here, a horizontal line, sorry, and it crosses at 2 points. So that's it. It's now 1 to 1. Does that make sense? Remember, not vertical, horizontal. Vertical is for function. All of these are functions. They pass the vertical line test. Now this one does not pass horizontal line test. Okay, how about number 2? It is, right? No matter what horizontal line I draw, it will only cross the graph at one point. Everybody understand this? Yes. It is 1-to-1. And how about number 3? Same thing, right? So no matter what horizontal line I draw, either cross it or not at all. Like down here, it's not gonna cross it, okay? So yes, it is 1-to-1. Are you okay with this? Now, let me say something about the theorem that I said here. Notice that this theorem says that a function has an inverse if and only if it's 1-to-1. Now, something's happening here. What are number 1, number 3 supposed to do to each other? What's a square function supposed to do with the square root?
Cancel.
They're supposed to cancel each other, right? But they're supposed to be inverse, right? I mean, that's what canceling each other means. They're supposed to be inverse. So what are we talking about here? Because I'm telling you that x squared is not 1-to-1, and therefore it should not have an inverse, right? And then yet you can tell me, well, what about a square root? Isn't the square root supposed to cancel this x squared? What's the catch?
There's a domain restriction.
Very good. Very good. The catch is that when you do square root of something, the answer is always what? It's always positive, okay? So for example, here if you plug in 1 and -1, the output is always 1, right? But imagine that you enter -1. 1 is gonna come in. But then what happens when you do square root? What do you get? What's square root of 1?
1.
Positive 1. You're not gonna get -1 back. So the square root does not see what's happening on this side. Do you understand this? So technically, this function doesn't have an inverse. Now, what you can do, and this is typically what we do when you study trigonometry, you're gonna do this with all the trigonometric functions, okay? Because none of the trigonometric functions are 1-to-1. But there is a notion of inverse of those. So what do? We make them 1-to-1. How do you make a function 1-to-1? You restrict the domain. So you restrict the domain to force it 1-to-1. For example, here you have the x squared function. Okay, it's not 1-to-1, but what's the issue? That something on the right, it has a mirror image on the left. So really, this is something that you don't need. So we can just ignore this half of the picture. You understand this? Now, when you do this, of course, you're creating a new function. It's an x squared function, but now the domain is from 0 to infinity. So, note, y equal x squared is now 1-to-1, and so it does not have an inverse. But we may restrict its domain. It's called restricting the domain. We may restrict its domain to make it 1-to-1. So, and graphically what we do is, okay, I don't really need the whole thing. I just need to look at this part, okay? So if you look at this part, notice that this is now 1-to-1. This passes the horizontal line test. Do you understand this? So the formula here would be f of x equals x squared, but with the condition that x has to be greater than or equal than 0. Now this is 1-to-1. Now this is 1-to-1. It passes the horizontal line test. It's 1-to-1, and it has an inverse. What's the inverse? What's the inverse of this? The square root function. So the square root function technically is not the inverse of the square function. It's the inverse of the restricted square function. What restriction? From 0 to infinity. So as a standard procedure that we do, if you have a function that's not 1-to-1 and you want to talk about an inverse of that expression, you have just to pay a price. What is it? Restrict its domain to force it to be 1-to-1. Okay? So you're gonna see this in trigonometry if any of you have to take that course. Okay. Any questions? Okay, so now that we know when a 1-to-1, when an inverse function exists, we know that we're gonna have an inverse function if it is 1-to-1. So let's say that you already know the function is 1-to-1. Okay, how do you find the inverse? Okay, so how do you find the inverse of a function? So let's do an example of this. So finding inverse And let's see. I'm gonna look at the very first example, and then we're gonna get an idea of how to find the inverse, and then we're gonna do more examples. Let's see. Number one, we had a function that was 1-to-1, and then instead of writing the picture, I'm gonna write it as a set of ordered pairs. Okay. So it's this function f. So as a function 2,7, 3, -1, 4,2, and 5,8. Okay. I'm gonna write that function. Remember, functions are relation, and then they may show up as set of ordered pairs. So 2,7, 3, -1, 4,2, and 5,8. This is a function. So we know it's 1-to-1. You can verify that two different inputs always have different outputs. You can do that visually in there by looking at it. So now it has an inverse. What is it? So what's the inverse of this function? 7, 2.
-1, 3,
-1, 3.
2, 4, and 8, 5.
2, 4, and 8, 5. In other words, when you're given something like this, to find the inverse, once you make sure that this is 1-to-1, to find the inverse, all you have to do is flip the other pairs, right? You just go and you start flipping, everybody. Everybody okay with this? Okay, so let's see, what is it that we are really doing? So for example, what does 2 represent? If we think about the notation y equals f of x, right? What does the number 2 represent? It represents x or y? What does it represent? X. And what does 7 represent? The y. So if you want to find the inverse, what is it that you're supposed to do? You switch x and y, right? Because when you find the inverse, then what happens is that if you do f inverse of y, that has to be equal to x, right? In other words, the output that was y now becomes the input, and then the input that was x now becomes the output of a new function. Does that make sense? So the role of x and y are switched. These have there are some things that we can say from here. For example, we can now write down a systematic way of finding inverse when you're given a formula. And also, there's something that's happening between domain and range. For example, what can you say about the domain of the inverse? In this case, what would be the domain of the inverse? And what's the y? The range of f, right? And what can you say about the range of the inverse? Now the range is given by x. And what's x? The domain of f. So when you find the inverse, you're switching domain and range. You understand this? Because you switch x and y, what you do is you switch domain and range. So I guess, let me say that as well. So, theorem, let y equal f of x, be a 1-to-1 function. So I'm saying this so that we can talk about its inverse, okay? Then what we can say for sure is that we know exactly what the domain of the inverse is going to be, and we know exactly what the range of the inverse is going to be. We don't even need to compute it, as long as you know the corresponding information for f. So domain of the inverse, what is it? What's the domain of the inverse?
7, -1, 2,
No. This is in general now. This is not here. So I'm not talking about the example anymore. So domain of the inverse, what is it? Is a range of f. And the range of the inverse is the domain of f. Okay? So what this means, as we did in this little example, is that actually we're switching x and y. So let me write down the steps. So steps to find a formula for f inverse of x. So here's what we do. So number one, you write y equals f of x. In other words, typically you're going to be given a formula f of x equals something. Well, instead of f of x, write y. Okay? So write y equal f of x. You're going to have an equation now. So then step number 2, what you're going to do is you switch x and y. Right? In the equation, you swap them. Wherever you see an X, you put a Y. Wherever you see a Y, you put an X. Okay? That's like what we're doing here. That's what we're doing here by flipping the other traits. Okay? And then you're gonna have an equation, right, with X and Y. So now what you do is solve for Y. Okay? So now step number 3, solve for Y. In other words, write Y equals to something that only has X's in it. And then step number 4, replace Y for f inverse of X, and you have your formula. Okay? Because remember, you switch X and Y, so now your Y represents the output of the inverse. Okay? So Y is taking the place of X. Do you understand this? And remember that X is the output of the inverse. Okay, so let me show you this in an example. Let's see, I'm gonna do okay, so I'm gonna do one. I'm gonna do 2 examples, and then I'm gonna give you another one for you to try. And this, could get a little bit interesting when you have rational functions, for example. Let's see, find the inverse. Again, just like above. And let's do the one that we already know, just so you see this at work. And then I'm gonna do this one. Let's do, I don't know, 2x plus 1 over x minus 5. And then you will do this one. Okay, so solution. So by the way, when I'm telling you this, I'm kind of implying already that these functions are one-to-one and so on, okay? But, a problem would be, depending whether the function is one-to-one or not. If it is, then find the inverse, okay? Let's keep that. All right, so for the first one, we have f of x equals 2x plus 1. The first thing that we need to do is, instead of f, we want to have y. Okay, now what do we do? So we switch x and y, right? So switch yeah, thing is correct, right? Switch. So switch x and y. Okay, so that means that we get x equals 2y plus 1. And now solve for y. That's it. So we get then the 2y is x minus 1. So y is x minus 1 over 2, which of course means 1/2 x minus 1/2. And now what we do, the last step, is replace y for f inverse. So f inverse of x is 1/2 x minus 1/2. As we saw earlier, that was our function g, that was the inverse of the function 2x plus 1. Questions? All right, so let me do a rational function sample. So I wrote here 2x plus 1 over x minus 5. 2x plus 1 over x minus 5. Again, same idea. So we have y equals 2x plus 1 over x minus 5. Now we need to switch x and y. So x equals 2y plus 1 over y minus 5. And now our job is to solve for y. Okay, I'm going to go here. So I'm going to multiply, distribute, then all the y's to one side, x's to the other. Factor out y over here. Now divide. So I get 5x plus 1 over x minus 2. So the inverse function is this formula. Now, when you do something like this, you may wonder, well, did I make a mistake, or something went wrong along the way, and so on. What I'm about to do, it doesn't really ensure that you're 100% right, but at least it gives you some confidence that the formula that you came up with is indeed the inverse. So, if this formula is supposed to be the inverse, then we can just pick an example, okay? Just pick an input, and then whatever plug into f, and then that output, if you plug it into your formula, is supposed to get back the original input, okay? So, for example, something what would be something easy to plug in into f? So let's see, we can plug in 0, right? So x equals 0 is a very easy thing to plug in. So this is, I'm gonna put in quotation mark because not a full check, but at least it will give us some confidence that the formula works, okay? So I'm gonna start with an x equal to 0. So, okay, so actually I'm gonna do f of 0. So f of 0 is gonna be -1/5, right? And you put 0 into f, you get 1 on top and -5 in the bottom. So then, what I'm gonna do is, I'm gonna plug in this into the inverse formula that we found out, and then let's see what we get. So it's gonna be 5, and then put -1/5 here, and here. So what do we get here? So on top we get a -1, so -1 plus 1 over -1/5 minus 2. I don't care what happens in the bottom. The point is that the top becomes 0, and 0 divided by whatever is just 0. Yes? So that means that 0 comes in, -1/5 comes out, that goes into the inverse, and I get back 0. So, because this is the same as this, now at least I have some confidence that that formula is supposed to do doing what it's supposed to do. Okay? Now, whether this is happening for sure or not, this is the word that tells you that this happens regardless of x and y. Okay? But, you know, you can do this little calculation to trust a little bit the formula that you're obtaining. Okay, any questions? No? Okay, good. Also, I guess something that you can easily do is, if you switch, let's see, I'm going to talk about the graph soon, but let's talk about it right now. If you're switching x and y, what do you think that happens? Let's say, these are rational functions. So rational functions have special lines, vertical and horizontal asymptotes. You did this in the test today, right? So if you find the inverse, what you're doing is you're switching x and y. So when you do the switch, what do you think happens to asymptotes? Yes?
The vertical asymptotes become horizontal asymptotes, and the horizontal asymptotes become vertical.
Very good, right? You remember, the vertical line is x equals something. When you switch, now it becomes y equals that something. So vertical becomes horizontal. Similarly, horizontal is y equals a number. You switch, now all of a sudden is x equals a number, right? So horizontal becomes vertical. So for example, here, what's the vertical asymptote of this line? Of this function? X equals 5, right? So what is that supposed to be for our function, for the inverse? It's supposed to be a horizontal asymptote now. Is it true? Is y equals 5 a horizontal asymptote for a formula? Yes, it is. Degree of the top, I mean, you should know this by heart. You did a test on this today. Degree of the top is the same as the bottom, so it's 5 over 1, right? Also, what's the horizontal asymptote here? 2, y equals 2. What's the vertical asymptote over here? X equals 2, because that's the 0 of the denominator. So we also see that the asymptotes are switching what they're supposed to do. This also gives you some confidence that your formula makes sense. Do you understand this? Okay, so let's see, try the other one. F of x equals 2 over x minus 1. This one is less complicated because the numerator is just a number. It's not a little polynomial. Do you have a formula for the inverse?
Yes.
What is it?
2 plus x over x.
2 plus x over x. All right. So let's see. Let's do a quick check. What's the vertical asymptote here? 1. What's the horizontal asymptote here? 1 over 1. Yes. Degrees are the same. So it's 1 over 1. So makes sense. Yes, makes sense. So what's the horizontal asymptote over here? There's a horizontal asymptote. What is it? Y equals 0. What's the vertical asymptote over here?
0.
X equals 0. The 0 is the denominator. Yes? So makes sense. At least the asymptotic behavior is working, so you could trust that function. Now you could plug in some points to check. But anyways, let's compute. So again, y equals 2 over x minus 1, switch, and then solve. So x times y minus 1 is equal to 2. Distribute, move the x over, divide. Okay? Any questions? Okay, so given a function, if you have the formula, now you know the procedure to figure out the inverse. How about the graph? Is there a relationship between an inverse, between a function, the graph of a function, and the graph of its inverse? In other words, if you know how a function looks, could you predict how the inverse is going to look? What do you think is going to happen? So, a graph of the inverse function. And again, let's do this with a little example, okay? And the example is going to tell us exactly what happens. So we have our little function f, you know, the one that we started from the very beginning, which is, what are the pairs? 2, 7, 3, -1, 4, 2, 5, 8. Okay, and then we know that this has an inverse and is a function 7, 2, -1, 3, 2, 4, and then a 5, right? It's the inverse. So let's go ahead and let's graph the function f and let's graph the inverse on the same picture, and then hopefully we're going to notice something. All right, let's see. Just to have something somewhat decent, let's try to have a graphing paper. Smaller. Okay, so let's do our x and y. Okay, we don't have too many negatives. Should be good enough. Okay, so let's see. I'm gonna remember the graph of this. How does the graph of the function f looks like? How will it look like? These are just dots, right? Just points. That's it. They're just a bunch of, like 4 points, right? So we have 2, 7. So here is 2. Then 1, 2, 3, 4, 5, 6, 7. So that's a point right here. Okay, so 2, 7, then 3, -1. Here's 3, here's -1. So that's this guy. Then 4, 2. Here's 4, here's 2. And then we have 5, 8. So 5, 8. So that's the graph of the function f. Okay, now let's graph the inverse. So the inverse is, remember, you have to flip x and y. So for example, this point is 2, 4. It's going to give you 4. It's 4, 2 is going to give you 2, 4, right? Or let me do it in order. So the point 2, 7 give you 7, 2. So 6, 7, 2. So we have to keep going here. We have this guy. Then -1, 3. That comes from 3, -1. Okay. So -1, 3. It's right here. Then 2, 4. That comes from 4, 2. And then 8, 5. That comes from 5, 8. So 8, 5. Okay. So we have the function f and the inverse function plotted on the same plane. Now, let's go ahead and let's do the following. I'm going to draw the line y equal x. The reason why I'm drawing this line is because this line is special. Who can tell me what's special about this line? Yes?
It's its own inverse.
Very good. It's its own inverse. In other words, if you are finding the inverse of a function, and this function has points on the line y equal x, what's going to happen when you do the inverse? Will those points move? They're not going to move. They're going to stay there. Because if you think about it as order pair, that would be a point of the form, let's say 2, 2 or 3, 3. When you flip it, it's still 2, 2, 3, 3. Do you understand this? X, x is x, x if you flip it. So that's a special line when you do this operation of switching x and y, because we call that line is invariant under this operation. Okay? It doesn't change. Okay? So I'm going to draw it. I'm going to draw this line. So as a line y equal x. And now let us take a look and see what's going on. For example, we had the point 2, 7, right? Which is this point here. And what happened to the point 2, 7? Where did it go to when we did the flipping? So where did this point 2, 7 go to? It went to 7, 2. So this point came over here. Yes? All right. Now the point 3, -1. That is, what is 3, -1? So this one right here. Where did it go to? -1, 3. So it went from here to here. Yes? So this point did this. And we did this action. Then 4, 2 became 2, 4. So 4, 2 became 2, 4. This guy went there. And then 5, 8 became 8, 5. This guy came here. So just at first glance, what's the first thing that you see? When we do this inverse operation, what's the first thing that you see? Good. Okay, so that's the first nice. I would say that's the second thing that you see. There is a simple thing to say. Basically, anything that was on top of the line y equal x went below it, and the other way around as well. Things that were below the line y equal x now move to the top of the line y equal x. Do you see that? And moreover, this is not happening randomly, like whatever you want. But what we really have is a reflection. In other words, if you look at this distance, so this distance right here, remember the distance there is a precise definition of distance. The distance is just the perpendicular between the point and the line. If you look at this distance, let me use a ruler. So, right there, and notice how this is 45 degrees as well, okay? So, that means that if I do this, okay, if this line that I'm drawing is a 45-degree line, that means that this is 90 degrees and this is 90 degrees, okay? So, in other words, the distance between a point and a line is a perpendicular line that joins the point and that line. And then what's happening is that if you measure this distance, it's going to be exactly the same as this distance over here. Okay? And same thing for the other. The distance between the red dot and the blue line, the line y equal x, is the same as this distance over here. So this flipping is not happening arbitrarily, it's actually symmetrical. In other words, the function f is being reflected over the line y equal x. Okay? And that graph, that reflection is what you get for the inverse. In other words, if the function f is on top, then the inverse is going to be below this line. If there is portions of the graph of f that's below the line, then the inverse is going to go to the top. Do you understand this? And it's a reflection. So the remark here is, remark. So here we notice that the graph of f inverse is the reflection of f about the line y equal x. Okay, so in other words, i.e. f inverse Yeah, it's reflected. I was gonna say symmetric with respect to a line y equal x to f, but that's just a redundant statement. Okay, so, and in fact, this is not just true for this example, this is true in general. This is a theory. So, if you know the graph of a function, if you want to know its inverse, how it looks like, you know the line y equal x, and reflect. Okay, so this is actually a theory. So, this is really a theory. Okay, so let me do another example. Suppose that you have the function f of x equals x squared with x greater than or equal than 0. And again, this is an example, you know, something that you know. So if I do my x and y, x, this is y, as you know, it goes to this, then 1, 2, 3, 4, so on. So this is the graph of the function f. Let's go ahead and let's draw the inverse. I mean, you know exactly what we're expecting, but let's see this happen. So if we are going to do this a little bit more parabolic, okay, so if we're going to draw the inverse, then what you should do is draw the line y equal x. It goes to all these points. 45 degrees. Come on, one more. So draw the line y equal x. That's the line y equal x, and then just do the reflection. So let's see. Here, this thing is not coming out the way I want it to come out. So let me do it again. This needs to be more nice. Oh, something like that. Okay, so when you draw the line y equal x, then what happens is that everything that is under the line has to be on top, and whatever is on top has to be under the line, but in a symmetric way. And then from here, you can easily see what to do. So this bottom part here, then reflects like that, and then the other part, you know, this point, for example, this is 2,4, goes to 4,2. So it's going to go here, 1, 2, 3, 4. Oops. So we're going to get this sort of shape. You know, and basically the point is that this little part becomes this one, and then this part right here reflects like so. Okay? And that's the reason why, you know, when you draw a square root, this is how it looks. It's a reflection of this picture. Okay? Also, if you plot points, you get the shape, but now you know a more general reason because it's a reflection of the x squared shape. Okay? All right, and then, you know, this is the inverse, which of course, you know, is our square root function. Okay, questions about finding the graph of an inverse? The reason I'm doing this is because now I'm going to introduce to you exponential functions. When I define logarithm, I will just say this is the inverse of the exponential, and therefore, since you know how exponential looks, you're gonna know automatically how logarithms look. Okay? If you know domain and range for exponential, then you're gonna know domain and range for logarithms, and so on and so forth. Okay? So now we're going to use all of these properties to our advantage.